Right. So this is going to be the second part of resampling methods, right? So it is something called the Bootstrap method, and it's part of resampling methods. As you remember, our resampling methods, they are divided into. So resampling methods, they're divided into cross-validation, right? Cross-validation and bootstrap. And for cross-validation, we had the first method, which was just a validation set. We discussed this validation set, and we had the leave one out cross-validation, and we had the k-fold. That's what we were discussing. Now we move on to the bootstrap, and this is just going to be the last video for this chapter. It's going to be the last video for this chapter, and then we move on to a lab after that. It's a very short chapter, sweet and nice, right? So let's discuss this bootstrap method. So this bootstrap method, we said it can be used to quantify uncertainty associated with a given estimator. So uncertainty associated with a given estimator. I think we understand what it means from our linear regression model. Remember, it was supposed to be like this, right? So this is the estimate plus B2x plus all the way up, let's say, to BPXP, right? So we wanted to know what is the uncertainty associated with each estimator like this. What is the associated uncertainty with, let's say, this estimator for B or for beta 1? What is the associated one? Uncertainty. So by talking about uncertainty, what we're basically talking about is us estimating the standard error, of the estimated coefficient, right, of the estimated coefficient. You remember this standard error, this SE, that we would use like SE beta 1. You remember when you're doing regression, would use like SE beta 1. This is how we can estimate the standard error using the bootstrap. We can use the bootstrap method, right? Some people might say R already gives us these things. Yes, R can already give you the standard errors and stuff like that, but it might be useful for you to understand the bootstrap, because some methods might be difficult for you to obtain, for R to obtain these measures of variability and stuff like that. It might be difficult for R to split them out, or R doesn't split them out. So it might be interesting for us to just discuss what it means, what the bootstrap is. So let's give an example. Let's say we want to invest a sum of money into two assets, right? Into two assets that yield returns. So we have two assets. We have asset number 1. Let's just say asset 1, and then asset number 2. This is what we want to. So the returns. This one, the return is X, and for asset number 2, the return on that is Y, right? So X and Y, they are random quantities. They are going to be random quantities, right? So if we put fraction of our money, let's say we have a sum of money. If we put alpha, let me not use dollars. We use rands. Yeah, we use rands. So if we put alpha rands, or fraction, let's say 3/4. If alpha is 3/4, so this is a fraction. It's a fraction. So if we put alpha fraction of our rands into asset number 1, it means asset number 2 is going to receive 1 minus alpha. Because if we say 3/4 goes into asset number 1, it means asset number 2 is going to get 1 minus 3/4, which is just a quarter, right? Cool. So since there's variability associated with the two returns on these two assets, we want to choose alpha to minimize the risk or the variance, right, of our investment. So what we're basically trying to do is we want to minimize the variance, that is minimize the variance of our investment, which is variance of the return that we get from that fraction that we put in asset number 1, plus the return that we get from putting that fraction in Y. putting the fraction y. So we want to minimize that variance. Of course, we don't want it to vary that much, right? We want to minimize that variance. If mathematically or in a bonus video, we are going to show that the variance here is minimized by alpha when alpha is given by this. When alpha is given by this, let me write the complicated formula here. In a bonus video, we can discuss how we get to this part here. So this, therefore, our alpha, we should invest our alpha like this. Our alpha should be defined by this, where this is going to be the variance of x, the variance of the returns, the variance of the x return of asset number 1's returns. That's the variance of asset number 1's returns, and then 2 will be the variance of or this symbol here will be the variance of the y or asset number 2's returns. So the variance of asset number 2's returns, and then this one here, this term here is going to be the covariance of our x and our y returns. The covariance of our x and our y returns, right? So it's basically the correlation in the returns. This is going to measure the correlation in the returns. Are there any correlations between the returns that we get from asset number 1 and the asset number 2? They are measured that way. Right? I think that part sort of like makes sense, isn't it? So what we are going to do is, in reality, these values are really not known for sure. Like for you to know 100% what they are, we really do not know what they are, because otherwise, if we knew the variances and stuff like that, our investments would be easy for everyone, because we'd know the values and then we'll just plug them in, and then everyone's going to make money. But the truth is, in reality, the variances or how our returns are going to vary, we really do not know what they are 100% with 100% accuracy. So we need to estimate them to a certain degree that we are comfortable with, right? So let's see how we can do that. We can use a past data set, or data set that we have. We can use the data set that we have with past measurements of the returns that we got from asset number 1. We have a data set that is our returns from asset number 1, and we have our returns from asset number 2, right? And we can use that data set to sort of calculate these estimates. So we are going to come up with an estimate for this variance, and we're going to come up with an estimate for this variance and an estimate for this covariance, like that. And then we plug this in to the formula. So here, instead of this actual one, we just plug this in. Instead of this actual one, we plug this in. Instead of this actual one, we plug that in. We plug that in. We plug the estimates. We just plug the estimates, right? What we can do is we can repeatedly do this process. So here what we can say is, all right, cool. We can use the whole data set. Or we can be statisticians and say, let's get samples. So we can get sample number 1. We can get sample 1. That will lead to the estimates 1. Estimate 1 and then 1. And this will lead to our alpha 1, an estimated alpha 1. And then we take another sample. That is going to be sample number 2. That's going to lead to the second estimates. And then we get our alpha 2. And we take a third sample and we estimate again. And then we'll get alpha 3. All the way up to, let's just say, n. N could be equal to 1000. We can repeat this process 1000 times and we get our alpha 1000. And what we can do now is to say, okay, what is the average of these fractions here? So we add up all the fractions that we got for alpha, and then we divide by 1000. So basically what we are going to do is we are going to get the alpha, the ultimate estimation for alpha is just going to be 1 over 1000 summation of equal to 1000 for our alpha I estimates, or estimates like that. Basically we just get the mean of the estimated alphas. right? As mean of the estimated alphas. What we have discussed here, it is essentially Bootstrap. It is essentially Bootstrap. And the standard error can now be estimated using this. Standard error of alpha can be estimated using, in our case here, it's going to be 1 over 1000 minus 1 subtracted by, not subtracted by, summation of I equal to 1000 of alpha I minus squared. So this alpha that we have with that, this of the ultimate estimator is going to come here. The ultimate estimator is going to come there, or the mean of the estimated alphas, of the estimated alphas, right? So here it's going to be our estimated alpha minus the mean of the estimated alphas. This is going to be our standard error of our alpha. That's how we estimate our standard error. So cool. Generally, so this is what the Bootstrap is. But let's generalize it to any estimator. Let's generalize it. This was an example, right? So let's write it generally. Generally, what are we saying here? Generally, what we're saying is, let's just say, we're going to use another example, but it's going to be more general than the previous one. So imagine we have a data set called Z. We call that data set Z, right? When we have our data set Z, it has an observation. It has 3 observations. 1, 2, 3. And let's say we have our X, we have our Y. Our X and our Y are going to be whatever they are. The predictors, whatever they are, right? So here it's going to be, let's say this is 4.3. And then for our first observation, our Y predictor is going to be 2.4. And then here we have 2.1 and 5.3 for our third one, and here we have 1.1, and here we have 2.8. So this is, let's say this is our table. That is our data set. That is our data set. Our data set, right? So what we are going to do is we are going to randomly select n observations from this data set in order to produce a Bootstrap dataset number 1. It's going to be Bootstrap dataset number 1. Just like the sample that we had. We created so many samples, right? We created sample number 1 with the alpha. Sample number 2, sample number 3. So that's what we're going to do here. From our dataset here, the Z, we are going to create a sample, a Bootstrap. This is just going to highlight like a Bootstrap set number 1, and we're going to get our, let's say, n observations. Here let's get 3 observations. Let's just get 3 observations. But here the Z can be n. We do not care. It can be n. It can be n, right? It can be n. So if our n is 1000, let's get 1000. Let's get 1000 observations from this Z. So we're going to get 3 observations, because our case here, our n is equal to 3. Our n is equal to 3 to create our Z star 1. Our Z star 1. So our Z star 1 is going to be something like this: observation, and then X, Y. So let's get 3 observations. We randomly select. That is very important. We are going to randomly select. Very important part. It's random selection. And another very important part of Bootstrap is we are going to do it with replacement. We are going to select with replacement. What does that mean? So let's say when we are creating our Z star 1, the first observation that we pick randomly is going to be observation number 3. So what is the X for observation number 3 is going to be 5.3, and then it's going to be 2.8. And we replace that into our data set. What it basically means is we do not say, we've picked observation number 3, so we are not going to pick it again. No, we are not going to say that. We are going to keep it there. We can pick it again because we are doing with replacement. It's still there in our data set. It can still be picked again. So we are going to do that. Let's say now when we pick the second observation for our Z star 1, we pick number 1. So number 1 is going to come in the database, into our data set, I mean. And let's say for the third part, we pick number 3 again. It's going to come in. It's going to come in like that. It's going to come in like that. It's going to come in like that. So this becomes our Z star 1. We can repeat this process and then get our Z star 2. Z star 2. Remember the samples that we're doing for alpha. That's basically what we do in Bootstrap. In Bootstrap, we randomly select from the same data set, but with replacement like that, with replacement. So let's say here we pick number 2. It's going to be 2.1 and 1.1. And then we pick observation number 3. It's going to be 5.3. And here it's going to be 2.8. And then we pick observation number 1. It's going to be 4.3 and 2.4. So what we see here is when you're creating these bootstrap samples here, sometimes your bootstrap sample might not have an observation. Like here we didn't have 2. 2 was not there. It does not matter. So it does not matter as long as you replace and you pick and you create your bootstrap samples to have n observations. It does not matter. You randomly do it with replacement, pick n random observations. It does not matter. You're creating your bootstrap samples like that. It works perfectly. So you can repeat this process, right? Let's say we repeat this process b times. We repeat this process b times. So z being an integer, b can be 1000, like in the alpha case. In the alpha case where we're doing those investment, b was equal to 1000. So here we are doing it b times. So let's say your b can be like this. Your b bootstrap sample, or not like sample, but your data set. Your data set, bootstrap data set will be, let's say, composed of 2, 2, 1. It basically means 2.1. Here it's going to be 1.1, and then 2.1, and then 1. We repeat number 2. 4.3 and 2.4. And like I emphasize, it does not matter that your sample or your set, doesn't matter that it doesn't have number 3 or any observation. It does not matter. It does not matter. As long as it has n with replacement, it's perfect. It repeats others, it does not matter. It does not matter. So cool. Here we now have z star 1, z star 2, all the way up to z star b. These are our bootstrap data sets. They are bootstrap data sets. These ones here, bootstrap data sets, right? We have b bootstrap data sets. Cool. Now that we have b bootstrap data sets, what we can do is for each one of them, we can get our estimate for let's say our alpha 1, right? You can get an estimate for alpha 1. If we were fitting a linear regression model, we can fit a linear regression model and get our estimate for beta 1 corresponding to, let's say, this one here, x1, beta 1 and beta 2. We can get our estimates for beta 1 and beta 2, right? That's what we're basically saying when I'm saying alpha 1. So imagine our alpha here. It just means any estimator. So we can get an estimation for beta 1, beta 2. And this is coming from bootstrap number 1. This is coming from bootstrap number 1. The same thing is we fit the linear model again with bootstrap dataset number 2. And we get our samples beta 1 estimate from bootstrap number 2. Beta 2 estimate from bootstrap number 2. Same thing here. Beta 1 estimate from bootstrap dataset B, right? And then beta 2 estimate from bootstrap sample number B. Perfect, right? So which means now how many do we have? We have B beta 1 estimates from B bootstraps. Can you see? Right? We have those ones there. So what that means is for beta 1, the ultimate estimator, or we can now calculate the mean, just like we had the ultimate estimator for B for alpha. We can now say the ultimate estimator for B1 is going to be 1 over B summation of I equal to 1 up to B of beta 1 estimate from bootstrap I, like that. Bootstrap I. Here we are just basically getting the mean of all beta estimates from bootstrapped Bootstrap datasets. When we fit the model, we created our Bootstrap datasets, we fit the model, and then we get our betas from each of the Bootstrap datasets, and then we just add this beta 1 plus this beta 1 and plus this beta 1 from this sample, from this dataset, and we just get the mean. That is basically what we did here. We just get the mean, and this is letter number B being the number of bootstraps that we had, not beta. This is letter number B. I think it's self-explanatory, and then that's what we do, right? I think this makes sense, I hope, anyway. And then what we are going to do after that, we're going to get the standard error. The standard error, let me write it in this way. The standard error now for beta 1 estimate is going to be given by this formula here. 1 over b minus 1 summation of I equal to 1 up to b, just like previous one. And then here it's going to be beta 1 estimate I minus the beta 1 dash squared, just like that. So we get this big estimator here, and we put it there. So the ultimate estimator, or the mean of the estimations from the bootstrapped samples, the mean of the estimates from the bootstrapped samples, we put it there, and then we just subtract that. So which means each individual one is going to subtract the mean from all of them, and then we sum up all those differences. Over the b that we had. If we had 1000, sum up with the 1000, and then just divide by 1000 minus 1, the sum of that. And then now it means we have our standard error. We've estimated our standard error. Straightforward mathematics, I hope. Straightforward mathematics. Nothing very confusing about that, I hope. If there is something, you can comment on the video and we can discuss it there. But that's basically what the Bootstrap method is. It is very important that we run in our dataset. We have our large dataset, right? It is a resampling method because we are repeatedly picking samples. We are repeatedly picking samples and creating some samples or some datasets there that are going to have a length of n, the same as our original dataset. And we are going to do that randomly, right? Picking the observations, we are going to do that randomly. But when we do it randomly, we do not care whether something is going to be repeated. An observation is going to be repeated in each sample or in each bootstrap dataset. We do not care because we are doing it with replacement. We have chosen 3 first. We replace 3 in the original dataset. We will be able to choose it again. We'll be able to choose it again, right? If we replace it. If we didn't replace it, then when we get to this part, it's going to automatically get 2 because we haven't replaced anything. But it picked 3 again because we do it with replacement. And we repeat this process a couple of times. We repeat this process enough times, b times. This one here, it's an art. There's no science to say repeat it 1,000 times, 1,000,000 times. There's no science. You just test it out. You test it out to see how your model is working. So you repeat it a b times. And then you just apply these formulas that they are very, very easy to understand. I think you apply your linear model to, I'm using linear model as an example, but you apply your model to each bootstrap, and the parameters that you get there, you should get the not in value, but for each bootstrap sample, for each bootstrap set, get your parameters. For each one of them, to get your parameters, average out the parameters. Then for each one, that's the average that you're getting in. And then for each one, you can get the standard error for each parameter like this. You can get the standard error for each parameter like that. And I was using linear regression here because it's much easier to explain using linear regression. That's basically it. That is Bootstrap, and that is resampling methods. Those are the main resampling methods. There are many others, but these are the main ones for our introduction course. These are the main ones that we are going to discuss. the next video, we are going to do a lab and see these things, how R is going to spit these out. How is R going to handle this, and what results can we get from R without us getting to write all these equations. So stay tuned for that video. In the next and the next chapter that we'll then get into is going to talk about regularization. So how do we choose the best model, and how do we regularize our model? It's going to be it's a very, very fundamental chapter. So stay tuned for that, for the videos for that chapter.